Hello friends, I Professor Darshan Thakur from Terna Engineering College Dharashiv welcomes you on my YouTube channel for this subject head Control System Engineering. So friends, as far as our today's session is concerned, so with this session we will try to conclude this force voltage as well as force current analogy technique which is adopted by this mathematical modeling of control system phenomena. Means as you can see, the objective for our today's session is to draw the force voltage as well as the force current analogous circuit for that given mechanical system, right? That will be our objective, right? So from sake of observation, first what we need to do, whether it is a force voltage analogous circuit or the force current analogous circuit, first of all we need to recall the basic three elements of that mechanical systems. These elements are nothing but what? The mass, damper and spring. At the same time we need to recall the force equilibrium equation for that mass, that is nothing but what? The second order differentiation, the force equilibrium equation for damper, first order differentiation, and for that spring the proportionality constant followed by the desired displacement, right? So in this numerical, in order to attain these two objectives, one by one we will try to attain. So in that first step, what we need to do in order to draw the force voltage analogous circuit from the given mechanical system. So usually there are three basic steps by which we can draw the force voltage analogous circuit for this given mechanical system, right? So these three steps are nothing but what? In that first step we need to enlist the number of elements which are interconnected in that given mechanical system. So along with these elements we need to count there are how many number of displacements, right? In that first step, from sake of observation, we need to count there are how many number of masses, springs and dampers. In that second step, we need to draw the nodal diagram. From that collected information, we need to draw the nodal diagram, and from this nodal diagram we need to write the system equation. And from this system equation, when we apply the Laplace transform to this system equation by admiring either force voltage or the force current analogy, we can draw this force voltage analogous circuit. So these are the three basic steps which are involved in case of this numerical, right? So first of all, what we need to do, first of all we need to count or we need to map how many desired elements are there. So as you can see, there are two identical masses m1 and m2, and these are the associated displacements belongs to m1 and m2, which displacements x1 and x2. Apart from this, there are two springs k1 k2 denoted by this proportionality constant k, and there are two dampers denoted by this capital B, B1 and B2. Means totally there are how many elements? Totally there are 6 elements we are having with us, right? So out of these 6 elements, so for sake of moment I will rub these three basic steps. In that first step, we need to count we are having how many masses denoted by m, how many dampers and how many springs. So we will come to know there are two masses, two dampers and two springs. As we are having two masses, so there will be two displacements, x1 as well as x2 belongs to m1 and belongs to m2. So this is how this first step is to be completed. Then after that, in order to attain the second step, right, we need to understand key number of nodes is always equals to number of displacement, and number of displacement is always equals to number of mass. So as we are having two identical masses m1 and m2, there are two displacements x1 and x2. So we need to include the two major nodes in that nodal diagram, right? So if we draw the nodal diagram here like this will be, this first bubble represents the first displacement, and this second bubble represents the second displacement. The first displacement is x1 and second displacement is nothing but what? X2. This F indicates the direction of applied force, right, with respect to this reference axis or the ground axis. So one horizontal line we need to draw here like this, which represents the reference axis. Then after that, as I told you earlier, from this collected data somehow we need to complete the nodal diagram. So this M1 is associated with this X1 and the ground surface, right? M2 is associated with this X2 and ground surface. So in same manner we need to connect this M1 into this nodal diagram. This will be the mass number 1, which is connected in between X1 and ground surface. This will be the mass number 2, which is connected in between X2 and ground surface, right? Still we are lacking with 2 dampers and 2 springs, right? So out of this 2 damper and out of these 2 springs, right, the first spring and the first damper, these 2 elements are connected in between these 2 displacements. These 2 displacements means what? The lower end of this K1 as well as B1 is kept at X2, and the upper end of this K1 and B1 is being kept at this X1. Means these 2 elements are interconnected in between these 2 displacements, X1 as well as X2. So in same manner we need to show these 2 elements in that nodal diagram. So how it is to be done? Very simple, like this. I will take this shunt arm. In this shunt arm, in that first branch, this represents the the K1 spring number 1, and in that second arm, this will be the damper number 1. This is B1 and this is K1, right? So in this way, and see one important thing which remains, this will be the direction of applied force, right? Always we need to remember that the displacement will be taken place in the direction of applied force, right? If that force is applied in that downward direction, so obviously all the particles belongs to this M1 and M2 will undergo through a equal displacement in downward direction. So accordingly, the nature of this force, this symbol represents the applied force. By default, the nature of this force is incoming towards that node, that is nothing but what? X1. Now, as far as the remaining elements are concerned, those are nothing but what? The spring number 2 and the damper number 2. How these 2 elements are connected in that mechanical system? One end is kept at the reference axis and another end is kept at X2, right? So these are connected in between X2 and reference axis. So in this manner we need to show, if suppose here I will draw, see, that is nothing but what? The spring number 2, right? And this will be the damper number 2. That is nothing but what? K2, and this is nothing but what? B2. Here this arrow indicates the direction of force belongs to that particular branch, right? The direction of force belongs to that branch, right? So this is how this nodal diagram is to be completed. In this nodal diagram there are 6 elements. Out of that 6 elements there are 2 masses. These are the 2 displacements of these 2 masses, and the remaining elements are nothing but 2 springs and 2 dampers. Out of these 2 springs and 2 damper, first 2 elements, spring and dampers, are connected in between X1 and X2. The remaining spring and damper is connected in between X2 and ground surface. So this is the first step. Once that nodal diagram is being drawn, then after that what we need to do? We need to write the system equation, right? In order to write the system equation, we need to recall the force equilibrium equation of this mass, of this spring and of this damper. The force equilibrium equation for this mass is nothing but what? M into second order differentiation d square x upon dt square. For damper it is B into dx by dt, and for spring here I will write K into x. That we need to recall, right, in order to write the system equation. So we need to write the system equation. In order to write the system equation, we need to use the Kirchhoff current law terminology. According to this Kirchhoff current law terminology, the sum of incoming plus sum of outgoing currents are equals to 0, or summation of incoming currents equals to summation of outgoing currents, right? We need to adopt this KCL strategy in terms of forces. Means we need to observe कि at this particular node, as we are having two displacements, so we are having two nodes. We need to observe at each and every node how many branches are interconnected with each other. Let us quickly go through the position of this node 1. So at this node 1, as you can see, 1, 2, 3 and 4. There are 4 branches, those are being interconnected to each other. Out of that 4 branches, the force belongs to first branch is incoming towards that node, right? Then after that we need to do the hypothetical assumption, that is nothing but what? The forces belongs to remaining 3 branches are outgoing from that node, right? So in this way we need to write the KCL equation in terms of forces. So this KCL equation will become what here? Here I will write sum of incoming forces equals to outgoing force. So incoming force denoted by F, and the outgoing force belongs to this mass, spring and damper. In which manner we need to write? So for that purpose we need to recall the equilibrium equation. So this mass is associated with displacement x1, so accordingly it will become m1 times of d square x1 upon dt square plus. Now as far as this k1 and d1 are concerned, which are associated with x1 as well as x2, so the overall or the net displacement for this k1, it will become x1 minus x2 plus the net displacement for this d1 is first order differentiation d by dt followed by x1 minus x2, right? But when we apply the Laplace transform at the same time, when we recall the analogous term in case of this force voltage analogy, so in case of this force voltage analogy, this F is analogous to V, as we know. Already we had considered or already we had studied this force voltage analogy in the previous lecture. This mass is analogous to L, damper is analogous to R, and this spring is analogous to elasticity, the reciprocal of C, and this X is analogous to Q, right? Because according to that Faraday's law, this I equals to the rate of change of charge per unit time, dq by dt, right? So when we recall this force voltage analogous term, at the same time simultaneously we apply the Laplace transform to this statement, so it will become what? F is analogous to V, so in terms of S domain it will become V of S. M is analogous to L, so L1 into as we are having the second order differentiation, so S square into X, right, means displacement is analogous to Q, so directly I am writing here, so it will become L1 S square into Q1 of S, like this. K is analogous to 1 over C, so it is 1 over C1 followed by X is analogous to Q, Q1 of S minus Q2 of S plus this B is analogous to R, so R1 followed by first order differentiation, so S into Q1 of S minus Q2 of S, right? So in this equation, as I told you earlier, when we replace with this I, that is nothing but what? dq by dt, right? When we apply the Laplace transform, so it will become what? I of S, here I will write I of S into S times of Q of S, right? So what we need to do, we need to replace this quantity with this I of S. Which quantity? S into Q of S with I of S. So as a result of replacement, it will become what? V of S equals to L1 S into I1 of S plus 1 over C1 times of S into, because we don't have this S term, that's why it is being divided, it will become I1 of S minus I2 of S plus R into, basically it is R1, so R1 into S into Q of S is nothing but I of S, so it will become R1 into I1 of S minus I2 of S. This whole equation can be treated as a equation number 1. If we observe carefully this equation number 1, so the coefficient of L1 is I1, coefficient of 1 over C1 is I1 of S minus I2 of S, and the coefficient of R1 is also I1 minus I2, right? This coefficient plays very important role when we convert this system equation in this force voltage equivalent circuitry. So laterly we will try to discuss. Then after that, in same manner we need to observe that at node number 2 there are 1, 2, 3, 4 and 5 branches are there. Out of these 5 branches, the force belongs to these 2 branches in which K1 and B1, these 2 elements are being connected, which is incoming towards that node, and remaining forces are outgoing from that node. So in same manner we need to write this KVL equation. So as a result of this, it will become what? Here I will write K1 times of x1 minus x2 plus b1 times of d by dt into x1 minus x2 equals to the right hand side of this assignment operator, as we are having 3 elements which are connected or associated in between x2 and ground surface. So initially m, so it is mass number 2, so d square x2 upon dt square plus this damper b2 into d of dx2 upon dt plus k into x2, right? In that next step, just similar to the previous one, when we recall the analogous terms, force is analogous to V, M is analogous to L, B is analogous to R, K is analogous to 1 over C, and X is analogous to charge Q. And when we apply the Laplace transform, so it will become So when we apply the Laplace transform, at the same time we are replacing these mechanical elements with analogous electrical analogous terms. So this k is no more, it will become 1 over c1 into x is analogous to q. So when we apply Laplace transform to this, so it will become 1 over c1 into q1 of s minus q2 of s. Right, like this, plus this b is analogous to r, first order differentiation r1s into q1 of s minus q2 of s, right, equals to m is analogous to l, so l2 s square into q2 of s plus b is analogous to r, r2 s into q2 of s plus 1 over c2 into q2 of s, right? Then after that, similarly we need to replace this s into q of s with this I of s. As a result of replacement, it will become, we don't have s term, so it will get divided. So 1 over c1 times of s into I1 of s minus I2 of s plus r1 into I1 of s minus I2 of s, it will become. Then after that, L2 into s square, so it is square L2 times of s into I2 of s plus s into q of s, I of s, I2 of s plus 1 upon c2s into I2 of s, right? So this is how this equation will look like. Then after that, what we need to do, if suppose this is equation number B, capital B, right? And similarly, if suppose this is instead of 1, if suppose this is equation number capital A. So from these two equations, capital A and capital B, carefully just try to see as far as this right hand side is concerned. So the coefficient of 1 over c1 is nothing but what? Apart from this 1 by s, I1 of s minus I2 of s. The coefficient of R1 is again I1 of s minus I2 of s, which is just similar to, as far as this capital A is concerned, the term which is being written to the right hand side of this assignment operator, the whole term is L1 s into I1 of s, but the remaining two terms are just similar to the partial part of this capital B. Same statement is there, 1 over c1 into I1 of s minus I2 of s, R1 into I1 of s minus I2 of s. But the coefficient for this L1 is nothing but what? I1 of s, right? Means we are coming on to this conclusion ki through this L1 there will be a circulation of I1. Through this 1 over c1 there will be a circulation of I1 as well as I2. Through this R1, I1 as well as I2. Through this L2 there will be a circulation of I2 purely. Through this R2 circulation of I2, and through this 1 over c2 circulation of I2. So by taking into account our equivalent electrical circuit will become what? First we need to consider this element whose coefficient is nothing but what? I1 of s, whose value is nothing but L1. So this is how L1 will look like when we excite the circuitry with this voltage, right? So through this L1 there will be a circulation of I1, and as in this vertical arm this will be the C1, and this will be the R1. This will be R1 and this will be C1. In that intermediate part or remaining part there are three elements, L2, R2 and C2. Through these three elements there will be a circulation of I2, I2 and I2. So this will be L2, this will be the R2 and this will be C2, right? So this is how your circuit will look like. This is C1, this is R1. Through this element there will be a circulation of I1. Through this element there will be a circulation of I2. Through which element? This is L2, R2 and C2. So this is nothing but what? The force voltage analogous circuit. So when we compare this mechanical system with this electrical system, so at that time as there are two displacements, X is analogous to Q and S into Q is nothing but I. So there are two identical currents, I1 and I2. There are two masses, L1 and L2. M is analogous to L. There are two springs, right? So here spring is analogous to the C, 1 over C, elasticity C1 and C2, and damper analogous to resistance R1 and R2. So in this way, this force voltage analogous circuit is to be drawn. So I just hope that you had understand all these things, right? So in that next session, we will try to learn how to draw the force current analogous circuit. Thank you.